一次次开拓未知空间，一次次触碰认知边界，思想涌动，跨越山海。你期待着怎样的风景？
My name is David MacMillan. I'm here at Princeton University's Department of Chemistry, right outside the magnificent Frick Laboratory, where I do most of my research. 2 months ago, I won the Nobel Prize in Chemistry for 2021. I won it for this idea, asymmetric organocatalysis. Hello friends of Alibaba DAMO Academy. Welcome to DAMO X Time. So to understand more about this work and my passion for chemistry, follow me inside where we could explain how we're making molecules for a greener, more sustainable future. First of all, what is catalysis? Well, if you look around you right now, absolutely everything that's around you was made by a chemical reaction. And in fact, in this slide, you can see a picture of my desk in my office, and every single component, every single material which is in my office is made by a chemical reaction. Chemical reactions do not happen spontaneously. To show this, as a chemist, we usually use something that's called an energy diagram. This is the way I describe this to undergraduates when I'm teaching chemistry. And that is imagining every night that you came home, there'd be a large hill that you have to come over. To do this is obviously going to require a significant amount of energy. So what catalysis is a way of removing that barrier or reducing it, effectively putting a tunnel that goes through this hill and allows it to be so much easier for you to go home every single night. And that's exactly what catalysis does for chemical reactions. Catalysis makes existing reactions easier, faster, and allows new chemical reactions to take place. Now, there are many ways in which catalysis impacts our world. And this is one of the ways I'm going to show you here, I think is one of the most interesting. This is the population of our planet over the last 2,000 years. And you can see it's relatively flat for all of that time until the beginning of the 20th century. And you can see there's a sharp inflection where we jump all the way up to 8 billion people. Well, as it happens, you would not happen to have 8 billion people on Earth if it wasn't for this one catalytic reaction, converting nitrogen over into ammonia. So why is the production of ammonia so important? Well, it turns out without ammonia, we would not have enough food to allow 8 billion people to live on our planet right at this moment. Interestingly, if you think about your body for a moment, it turns out that 50% of all the building blocks which are in your body actually contain nitrogen which comes from this one catalytic reaction. So clearly, catalysis is important for our world. And in fact, 90% of industrial scale chemical reactions actually involve catalysis, and 35% of the world's GDP is based upon catalysis. And that number is only going to go up as we move towards more and more sustainable processes. In terms of how does catalysis impact your world, we've already talked about the need for food, but you can also think about it in terms of diagnostics, solar cell materials, medicines, and even the global manufacturing of materials is based upon catalysis. So clearly catalysis is extremely important. The next question is, what about asymmetric? If you think about your hands for a second, you can look at your hands and realize that they're mirror images of each other, which means they're similar, but they're not identical. We know they're not identical because you can take a glove, as shown here, and we know the left-hand glove fits on your left hand. But we know if you take the same glove and move it to your right hand doesn't recognize it. It turns out exactly the same phenomenon happens with organic molecules. They can exist as mirror images. If you think about how you can actually differentiate these mirror images in a lab setting, it's actually very difficult. At the present time, it would require equipment that would be expensive, extremely expensive to the point of being almost 400,000 yuan at the present time to be able to separate these two molecules. What's interesting, however, if I give these same two molecules to almost anyone on Earth, including this person here, this is a photograph of my daughter, Emma, when she was 3 years old, she can differentiate these molecules instantly just by smelling them. So why is that? Why is it so difficult to differentiate them in a lab, but so easy for a human to tell them apart? Well, it turns out that humans are made up of one mirror image and not the other mirror image in all the building blocks of life. Things like amino acids, nucleic acids, proteins, DNA, carbohydrates, hormones, they're all made from one mirror image, but they're not made from the other one. And that has very important implications for biology. For example, in medicine. Now, while your hands can be mirror images of each other, most medicines can also have a mirror image. And while one of those mirror images can be recognized by your body, the other one will not. And in fact, those can be toxic, if not dangerous. So as such, for this $100 billion economic market, it's extremely important that we can access one mirror image of a drug and not the other one. And the best way to do this is through catalysis, or more specifically, asymmetric catalysis, the idea of making one mirror image but not accessing the other image. The third part becomes, what about organo? What does organo mean? Well, to think about organo, I'm going to take you back to 1996. Why that? Why 1996? Well, this is where my part of the story begins. In 1996, I entered Harvard as a postdoc, and I learned an enormous amount being with Dave's team. Dave Evans is a genius. He's one of the most influential chemists that has ever lived, and he's also a master in this area of asymmetric catalysis. In particular, he worked in the area of metal catalysis, but in 1996, there was only two branches of asymmetric catalysis. There was biocatalysis, using enzymes to make single mirror images. There was metal catalysis. And here are some of the metals that Dave's group worked on. This contraption is a glove box. This is a box that emits or removes oxygen or air or moisture from the environment. And this is very important when you're working with metals. But while I was with Dave's team, every single day I would spend hours literally inside this glove box. And after 2 years, I started to think, why am I spending so much time in a glove box every single day? To understand this, I have to show you what a typical metal catalyst looks like. This is a typical metal catalyst. It contains both a metal and an organic component, as you can see here. This is the metal. They can be toxic, they can be difficult to work with. They do not exist happily out in the environment, and that's why you have to use glove boxes to work with them. And in many cases, they're not sustainable. Once you remove them from the earth, you can't put them back in again. In contrast, the organic molecule, the part on the left, those are typically inexpensive, they're safe, and they're sustainable. And as such, I started to think, what if we only use the organic part as the catalyst and not use the metal? And ultimately, this became known as organocatalysis. Okay, so in 1998, I landed a job as an assistant professor at Berkeley. And when I moved to Berkeley, this is one of the first photographs I took of my new group. I really love this photograph. Turns out it's on a Friday night, where this is a young lab. We're all in there trying to make an impact, trying to make a difference. What we decided we wanted to work on was this idea of organocatalysis. Now remember, there's only two branches that exist. There's biocatalysis, there's metals, so this was something that was completely different. And the reason we wanted to work on organocatalysis, because we felt the building blocks should be readily available, they should not be sensitive to air or moisture, they should be inexpensive, they should be easy to handle, you shouldn't have to use glove boxes to do any of this chemistry, and they should be non-toxic. They should be completely sustainable because they should go right back into the life cycle. But the main reason we wanted to work in this area, we wanted to develop a field of catalysis, something that would work for many, many, many different types of chemical reactions. Okay, so towards this, one day I was standing in lab and one of my students, shown here, Tristan Lambert, a first-year graduate student. Tristan is now a very successful professor at Cornell University. He walked up to me and said, "What is the mechanism of reductive amination?" This is a very simple organic reaction. Being a new professor, I ran to the board and I drew up, well, it involves a carbonyl that forms with an amine, it forms an iminium ion, and it's only when it forms the iminium ion does it have the electronic configuration to do subsequent chemistry. And right there, right then, is when I had my eureka moment. Because I realized you could take exactly that idea and use this with alpha, beta, unsaturated aldehydes to do a type of catalysis that would look very similar to what had already been accomplished using metals. Well, to draw this in a slightly more conventional way as shown here, you can see there's two equations. The top equation uses metals. And in that equation, there's many examples, more than 100 different reactions which had been successful using these types of catalysts. But the bottom one, using organic, there was no examples. But if these were simultaneous equations, all of the reactions that work at the top should also work for the organic ones at the bottom. But there was no examples of doing those at the time. So that was obviously something that was very exciting to us. So we set off to test this. We tested it using what's called the Diels-Alder reaction. This is actually the notebook from a first-year graduate student who ran the first organocatalytic reaction in my lab. Her name was Kateria Rent. And you can see here, the organocatalyst is the molecule that's sitting above the arrow. And when we perform this reaction, you'll see it scrolls all the way at the bottom, and the result is shown. It says, not racemic, not racemic. What does that mean? Well, this was unbelievably exciting to us. Non-racemic means it makes one mirror image in preference to the other mirror image. This was so exciting to me. When I heard this result, I walked into my office, I closed the door, I jumped up and down for 5 minutes. I remember calling my wife and saying, I think we just got tenure because this is such an exciting result. But when my feet came back to ground, you'll see at the top of this slide, there's another part of it. I realized it said it was 48% EE. What that means is 48% excess of one mirror image over the other one. And if the chemistry community was actually going to take us seriously, this number would have to be 90%. So we had to develop a new catalyst to do this. The new catalyst that we come up with is shown here. We liked it for 2 reasons. The first one was it was really cheap, really inexpensive. You can see it's actually made from phenylalanine, which is artificial sweetener. It's actually an amino acid, and it's combined with acetone. But the second reason we liked it is we thought it would allow us to make one mirror image. As you can see in this slide, that is exactly what happened, in greater than 90% EE. This was really, really exciting to us, and now we had to produce a manuscript. We had to tell the world about this, what we felt was a really exciting finding. So as I look back at our first paper, you can see I was a first-year assistant professor, and I'd sort of climbed to the highest mountaintop, and I wanted to yell at the world why we felt this was so important. And you can see that in the first paragraph, because I talk about the impacts on society, for academia, for industry, and for the economy. But the third part I was most proud about in this manuscript was we introduced the concept of a generic activation mode. You might wonder, what is a generic activation mode? Well, this is simply the idea we wanted this catalyst not to work for one reaction, but to work for many, many, many different reactions. So we set out to test this, and in fact, when we looked at this, first of all, we immediately had the Diels-Alder reaction. We only got to 3 different chemical reactions. So at this stage, we had to develop a second generation catalyst that would allow us to hopefully get many reactions to work. To do this, we introduced our second generation catalyst, which is the one which is shown here, and immediately we were off to the races. Many, many, many reactions were successful. Fortunately, also, Jorgensen and Hayashi introduced another catalyst that worked for iminium chemistry, and this really dramatically expanded the field even further. Okay, so over the last few months, many people have asked me about applications of organocatalysis. How does it impact our world? Well, it does so in many ways, and I thought I'd just give you a few examples. The first one is actually in the area of fragrances and perfumes. You might not know it, but perfumes are used on an enormous scale by the human race on a daily basis. Indeed, in northern India, they actually perform organocatalysis on a 300 metric ton scale, which allows you to make this perfume that smells of this beautiful rose scent. What other areas? Well, how about materials? This, as we know, is the plastic recyclable economy. We know that plastics are beginning to pollute our earth, and it's beginning to pollute our oceans. What Bob Weymouth and James Hedrick have been able to demonstrate is using organocatalysis, they can take plastics and they can break them back down into their monomers, which allows you to then remake them back into plastics. That's effectively making plastics recyclable, which is obviously extremely important for sustainability. But without question, the way in which organocatalysis has been most utilized is for medicines, it's for pharmaceuticals. I thought I'd just show you one example. This is talsedupant from Merck. This has been developed as a way to treat chronic migraines. And the reason I wanted to show this is this indeed uses iminium catalysis. Okay, but there's a fourth aspect to organocatalysis that we certainly did not envision, we certainly did not see coming, but one I think is very important. And it's something that's been called democratizing catalysis. Well, what does that mean? Well, democratizing catalysis just means that organocatalysis is affordable and accessible field to the world. People typically ask me, where does the future hold for organocatalysis? And quite honestly, I don't know the answer to that question. But I do have to say that we have to provide for our ever-expanding global population in a responsible way, and that includes using catalysis. And in this context, it's going to be based on organocatalysis, it's going to be based on biocatalysis, but also things such as photocatalysis and electrocatalysis are going to be essential as we build a sustainable planet. Thank you very much.